Good morning, viewers. Good morning, viewers. Today we'll be looking at physics, and we'll consider the concept of acceleration due to gravity, which is also the gravitational field intensity. This subtopic is under gravitational field. It's under gravitational field. So acceleration due to gravity or the gravitational field intensity. So the acceleration due to gravity, small g, is also known as the force per unit mass, small m, of an object, and is responsible for the weight or force an object experiences on the earth. So the acceleration due to gravity, small g, is also known as the force per unit mass, small m, of an object, and is responsible for the weight or force an object experiences on the earth. Full stop. Okay, so it says recall that F is equals to G m1 m2 over r squared. That is from Newton's law of universal gravitation. Okay, from Newton's law of universal gravitation. From Newton's law of universal gravitation, we have that F is equals to G m1 m2 over r squared from Newton's law of universal gravitation. Okay, then if m1 is equals to me, and that m2 is equals to a common m, and then we also have that r is equals to re. This is the mass of the earth, and this can be the mass of a satellite or an object revolving in space, and this is the radius of the earth, re. That means that this formula then changes. Formula changes. You have that F is equals to G MEM over RE square. You can call this equation 1. Okay, the formula then changes. You find out that the magnitude of the force of attraction between the 2 point masses, mass of the earth and the mass of a satellite, perhaps becomes GM over RE square. Also recall that F is equals to mg, that force is equals to mass times acceleration due to gravity. Okay, and if I make G subject of formula, I'm having that G is equals to F over m. That is, acceleration due to gravity is force per unit mass. G is force per unit mass. I can call this one equation 2. Okay, now if I substitute equation 1 into equation 2, you say substitute equation 1 into equation 2. Substitute 1 into equation 2. That means that in place of this F, I'll write the whole of this, and then my equation 2 changes. Equation 2 changes to G equals to capital G MEM over RE square all over m. Okay, that is this. In place of F, which is the force, in place of this force, I write this equation or that formula. Alright, so it then means that G will equals to G capital G MEM over RE square, okay, divided by m over 1, which means that small g will be equals to capital G MEM over RE square times 1 over m. Okay, when you change division to multiplication, you change the division sign to multiplication, you have to invert it, and by means of inversion, this one will go up and m will come down. So I'll be having 1 over m. Alright, I've inverted that. I'm having 1 over m. Now you see that m will cancel out m. We eliminate m, and small g equals to capital G ME over RE square, which I can call this equation 3. Then follows that the equation for gravitational acceleration or gravitational field intensity small g is equals to F over m, and is also equals to G me over RE square. Okay, we'll take note of this. Take note of this. Alright. Okay. Where so we see that me is called the mass of the earth measured in kilogram, RE is the radius of the earth measured in meters, capital G is the gravitational constant, and the gravitational constant capital G is 6.67 times 10 to the power minus 11 Newton meter square per kilogram square, and small g is the acceleration due to gravity in meters per second square. So take note of that. The formula for acceleration due to gravity or the gravitational field intensity is F over m equal to capital G me over RE square. So take note of that. Alright. It says the mass and weight of a body on Earth are 8 kg and 80 Newton respectively. Okay, so we take that. It said mass of body on Earth is 8 kg, and the weight of body on Earth is 80 Newton. Okay, the weight of the body on Earth is 80 Newton, while the mass of the body on Earth is 8 kg. So we have to determine the mass and weight of the body respectively on a planet. So determine the mass and weight of the body on a planet. You say mass of body on a planet, a different planet, that is MP. MP is unknown, and the weight of body on a planet is W, is also unknown. Alright, it says where the pull of gravity is 1 over 8 that on the earth. So it means that the pull of gravity on the planet is 1 over 8 of the pull of gravity on the earth's surface. Okay, and we know that the pull of gravity on the earth's surface is 9.8 meters per second square. Okay, the pull of gravity on the earth's surface is 9.8 meters per second square. It then means that the pull of gravity on the planet will be equals to 1 over 8 of 9.8 meters per second square. Alright, which is 1 over 8 times 9.8 meters per second square, which will give you 9.8 divided by 8. Okay, and I multiply 1 times this and I have 9.8 divided by 8. That would be, this gives me 1.225 meters per second square. Okay, so it means that the pull of gravity on the planet is 1.225 meters per second square. Okay, so we have gotten the value of the pull of gravity on the planet as 1.225 meters per second square. Now you should note that the mass of a body does not change, whether it is on the Earth's surface or it is on Mars, Venus, Jupiter, Pluto, any planet. The mass remains constant. So you see the mass of a body does not change. Okay, it remains constant. Okay, irrespective of the location. Irrespective of the location. So that means that the mass of the body on the planet MP is equals to the mass of body on the Earth's surface, which is 8 kilogram. And then we are asked to calculate the weight of that body on the planet. Now, if G is equals to F over M, it then implies that F will be equals to mg, and that F is similar or is equivalent to the weight. Okay, the force of gravity is similar to the weight of an object. It implies that W will be equals to mg, and W in this case is the weight of that object on the planet. So the weight of the object on the planet will be the mass of the object on that planet times the pull of gravity on that planet. And then we had the mass of that object as 8 kilogram, and then multiplying with the pull of gravity on the planet is 1.225 meters per second square. So when I multiply it, I'll be having 9.8 Newton, which is approximately 10 Newton to the nearest whole number. Okay, so this is the weight of the object on the planet. Okay, the weight of that object on the planet is this, 10 Newton. Alright, so quickly I'll explain again. It says that the mass of the body on the Earth is ME, which is 8 kilogram, and the weight of the body on Earth is W, that is 80 Newton. And the mass of the body on a planet is MP, which is unknown. The weight of body on the planet is W. And it was told us that the pull of gravity on the planet is 1/8 the pull of gravity on the Earth. That the pull, that is, it says where the pull of gravity is 1/8 that on the Earth. So it then means that GP is 1/8 of GE, and that GE will be equals to 9.8. Now we know the acceleration due to gravity on the Earth's surface is 9.8 meters per second square. Okay, it's 9.8 meters per second square. That GE is 9.8 meters per second square. So you find out that some textbooks approximate it to 10 meters per second square. So the acceleration due to gravity on the Earth's surface is this. Okay, so it then means that GP will be 1/8 of GE, which is 1/8 of 9.8. So if you change off to multiplication, 9.8 divided by 8 gives you 1.225. That is 1.225 meters per second square is the acceleration due to gravity on the planet, GP. So we have this as the mass, the mass of a body does not change. It says that the mass of the body does not change. It remains constant irrespective of the location. Irrespective of the location of that object, its mass does not change. It remains constant. So it means we have that the mass of the body on the planet will be the same thing as the mass of the body on the Earth. The mass of the body on the planet is similar to the mass of the body on the Earth, which is 8 kilogram. And if acceleration due to gravity is force per unit mass, that means that if you make F subject to formula, you cross multiply. M times G gives you what? Mg. It means that F will be equals to mg. And that also the force of gravity is similar to the weight of that object. Therefore, the weight of the object is mass times acceleration due to gravity. Now, the weight of the object on the planet will be mass of the object on that planet times the pull of gravity or the acceleration to gravity on the planet. The mass of the object is 8, it remains constant. The acceleration to gravity on the planet is 1.225. And when I multiply 8 times 1.225, it gives me 9.8 Newton, and approximately we have 10 Newton to the nearest whole number. Alright, so that is the weight of the object on the planet. So it means that therefore the mass of the object on the planet is 8 kilogram, and its weight on the planet is 10 Newton. Alright. The second question says that the Earth is 4 times the size of the Moon. The Earth is 4 times the size of the Moon. Now, it then means that the size there implies the mass. Okay, so you can say the mass of the Earth is 4 times the mass of the Moon. Okay, take note that the size there means mass. Size means mass. Okay, so the Earth is 4 times the size of the Moon. That means the mass of the Earth is 4 times the mass of the Moon, and the acceleration due to gravity on the Earth is 80 times that on the Moon. Okay, so we can take that down. You can say that ME is equals to 4 mm. You can call this one. And the acceleration due to gravity on the Earth is 80 times the acceleration due to gravity on the Moon. Okay, so it then means that GE will be equals to 80 GM. Okay, so the mass of the Earth is 4 times the mass of the Moon, and the acceleration due to gravity on the Earth is 80 times the acceleration due to gravity on the Moon. So we are asked to find the ratio of the mass of the Moon to the Earth. The ratio of the mass of the Moon to the mass of the Earth is unknown. Alright, so we'll come back again. We know that the formula for small g is capital G m over r square. Okay, we know that the acceleration due to gravity is capital G m over r square. So we'll look at that on the Earth's surface. We'll take that of the Earth's surface, say the acceleration due to gravity on the Earth's surface, acceleration due to gravity on Earth's surface, will be GE over equals to capital G ME over RE square. Okay, that is it. So it implies that we are going to make the substitution. Okay, and please take note, this size is the radius. Size deals with the radius. So that is the radius of the Earth is 4 times the radius of the Moon. Okay, the size here deals with the radius, not necessarily the mass. It deals with the radius. So radius of the Earth is 4 times the radius of the Moon. Okay, so if I now substitute it here in place of GE, I'll be writing 80 GM. Okay, so that means that this equation now will change. That is 80 GM will be equal to capital G times the mass of the Earth over the radius of the Earth now is 4 rm over 4 rm all raised to the power of 2. Okay, I'm having 80 gm equals to capital GME over 4 rm raised to the power of 2. So if I expand this now, I'm having 80 gm is equals to capital GME over 4 raised to the power of 2. 4 raised to the power of 2 is 16, and rm raised to the power of 2. So we'll be having 16 rm square. Okay, so if I cross multiply, I'll have that GME is equal to this is, if I cross multiply, that is 80 gm times 16 rm square. Alright, so 80 times 16 will give me 80 times 16 gives me, so 80 times 16 will give me 1280. 1280. And I'll have gm rm square is equals to capital GME. So if I then make this subject of formula, capital G equals to 1280 gm rm square divided by small e, a capital N E. Okay, so I can then call this one equation 3. Okay, so I've made my gravitational constant the subject of formula, which is 1280 gm, which is the acceleration due to gravity on the moon, and rm square, which is the radius of the moon, over ne, mass of the earth. Okay, now you also come back, we looked at the acceleration due to gravity on the earth, acceleration due to gravity on earth's surface. Now we look at the acceleration due to gravity. Let's look at acceleration due to gravity. Acceleration due to gravity on the moon. The acceleration due to gravity on the moon, and this will give us gm equals to capital G mm over m square. Okay, so if the acceleration due to gravity on the earth's surface is this, the acceleration due to gravity on the earth's surface is ge equals to gme over r square, then that on the moon surface will be gm over rm square. Okay, alright, so I can also make capital G the subject of formula, and I cross multiply. I'll have gm rm square is equals to gmm. Okay, I cross multiply, this will multiply this, and I'll have this is equals to gmm. Now if I divide by the coefficient of capital G, the coefficient is small m, so I'll be having capital G equals to gm rm square divided by mm, which I can call this one equation 4. So I divided by its coefficient, which is the mass of the moon, and I had this. Now we equate equation 3 to equation 4. So you equate 3 to 4, equation, so equate equation 3 to equation 4. So I'm having 1280 gm rm square over me is equals to gm rm square over mm. Okay, so this is it. This is equation 3. Equation 3 is 1280 gm rm square over me. I then equated it to equation 4. Equation 4 is gm rm square over mm. So I equate them, and then what am I eliminating? I'll eliminate this, eliminate this, I eliminate this one, eliminate this as well. Okay, so I'm left with 1280 over me is equals to 1 over mm. Then we are asked to find the ratio, of the mass of the moon to that of the earth. So this then becomes from this. So my equation now changes. If I put it in the form of fraction, that I will have mm over me. So to obtain mm, that mm over me will be equal to 1 over 1280. Okay, so this is it. That implies that mm ratio me is 1 ratio 1280. Okay, so the ratio of the mass of the moon to the mass of the earth is this. The ratio of the mass of the moon to the mass of the earth is 1:1280. Alright. Thank you.